let's go ahead and get started on the intermolecular forces. Let me get to the right spot here. Okay. So we talked again about this last year, so this is, I'm going to go through this fairly quickly because hopefully this is going to be a review for most of all of you. When we talk about intermolecular forces, we're talking about the bonds between molecules, not the bonds within a molecule. So, for example, right here, the bond in the HCl right here, that's a covalent bond. Okay, that's also called an intramolecular bond. But the bonds between HCl molecules are called intermolecular attractions. Okay, and excuse me, those are always a lot weaker than the intramolecular forces or the covalent bonds. So that's basically what we're talking about here. We're talking about the forces between the molecules that hold them together, and those are going to affect things like boiling point, melting point, those sorts of things. You're going to see lots of questions related to this on the AP exam that have to do with, which one would boil at the highest temperature or that sort of thing. So, okay, again, boiling point, vapor pressures, viscosities, melting points, that sort of thing. Okay. As a group, overall, these intermolecular forces are called van der Waals forces. Van der Waals was some scientist, I'm sure, and they put his name on something because he did something important. So anyway, also called van der Waals forces. Just keep that in mind because sometimes they will refer to it as that on the AP exam. The different types of van der Waals forces that we need to talk about, the main types: dipole-dipole, hydrogen bonding, and London dispersion. We're also going to talk a little bit about ion dipole, which we also talked about that last year. So. Nothing new there. Okay, so ion dipole is the first one that we'll talk about. These are going to be more important when we're talking about solutions. Solutions that have ions dissolved in them, okay? So you put sodium chloride into a solution. You're going to have these ion dipole interactions. And we talked about this a lot last year. I know that, at least for my classes, I showed you guys lots of pictures of what happens when you put salt, excuse me, too early in the morning. What happens when you put salt into water? The water molecules, so this could be an example of salt and water. You've got the positively charged sodium ions right there, and then you got the water molecules here, and the oxygen end, the negative end of the water molecule, is attracted to the positive end of the sodium and surrounds it. Okay, and then the positive end of the water is attracted to the negative end, the negative ion, the chlorine, and surrounds it. Okay, and so those ions get pulled apart from one another, and the water molecules surround them. And so that's an example of ion dipole interactions. And this is why ionic substances dissolve in polar solvents. Okay, so in other words, why salt or other ionic compounds will actually dissociate, dissolve in things like water. Okay, so dipole. This looks a lot more complicated here, but what's essentially happening there is you've got attraction and repulsion happening, okay? Because these are molecules that have an overall dipole moment. These are molecules that are polar, all right? And these polar molecules, when they're around one another, the positive end of the polar molecule is going to be attracted to the negative end of a different one, okay? But it's going to, the negative ends are going to repel, okay? So the dotted lines show the repulsions here, and the solid lines show the attractions. And so that's what's happening here. Not a lot of difficult ideas here. I mean, you just have positive attracted to negative, and these are going to be less strong than the intramolecular forces, than the covalent bond, but they are fairly strong. Okay. And these forces are important when the molecules are close to one another, okay? Because again, these aren't very strong charges. This isn't like an ionic compound where it's got a completely 1- or 1+ charge. These are partial charges, due to the unequal sharing of electrons. Okay, and so because of that, you're going to have a fairly weak charge, which means that it's only when they're close to one another that these forces actually become important. Okay. The more polar the molecule, the higher its boiling point. That kind of makes sense, right? So the dipole moment right here, that's a way of measuring how polar it is. So you can see propane, not very polar at all, okay? And so it has a low boiling point relative to these others. And then you get up to something like acetonitrile, dipole moment of 3.9, and the boiling point is up to 355. Now notice, they picked substances that all had very similar molecular weights, okay? So they all have about the same molar mass. The main thing that's really different about them is their polarity, okay? And so that affects their boiling point. Okay, London dispersion forces. Now we talked about this a little bit last year. Just want to make sure you understand why. This is sometimes called an instantaneous dipole. Now, the stuff we just talked about, the dipole-dipole interactions, that comes from molecules that permanently have poles on them because of the way that they share their electrons. You know, HCl, the chlorine is always going to pull the electrons closer to itself. So there's always going to be a partial negative charge on the chlorine side of that molecule. And there's always going to be a little bit of a positive charge on the hydrogen side of that molecule. Okay, so that's an example of one where it's kind of it's a permanent dipole. Now what happens here are temporary or instantaneous dipoles. Okay, so you got something like a helium atom. Now normally these electrons don't like to be on the same side of the atom or the same side of their orbital, but the electrons are just moving around constantly. Okay, and so every once in a while you'll get this situation where both electrons end up on the same side of the helium atom. Okay, and when that happens, now you have a little bit of a negative charge over on this side and a little bit of a positive charge on this side. Now this only happens for an instant, and then it's back to the way it was. So these are called instantaneous dipoles because the dipole forms, and then it unforms, and then it forms, and then it unforms, and it just keeps going like this as the electrons keep moving. Okay. So this is not a permanent dipole. This is just a momentary thing. Okay, so at that instant, the helium atom is polar, and just at that instant. Okay, now if at that instant there is a helium atom that is polar, and it comes into contact with another helium atom, okay, such as this one, then what happens there is the electrons here will repel these electrons, and they'll be attracted to the nucleus of this other helium atom, okay? And so they sort of induce a dipole. Induce means they essentially cause it in something else, okay? And so they come into contact with another helium atom, and there's this slight dipole moment that gets created there because of that instantaneous dipole on the other atom. And so then you have sort of this chain reaction where if one has a little bit of a dipole, it creates a dipole in atoms around it. Okay. Now again, this is all instantaneous. So this happens and then it stops. Happens and it stops. So these bonds form and break, form and break, form and break. So they're not very strong for that reason, especially with smaller atoms like helium. In fact, London dispersion forces are so weak for small molecules that helium is you have to get helium colder than any other element to turn it into a liquid from a gas. Helium does not want to, it's just not very attracted to other helium atoms. But there is a little bit of attraction here based on this induced dipole. Okay. So this is the instantaneous dipole that we're talking about here. That's coming from the instant when these two electrons are on the same side. And then again, the induced dipole is kind of the forced thing that happens on this other atom where this electron gets pushed over to this side because it's repelled by the electrons in the other helium. Okay? And so that's the idea there. One has an instantaneous dipole, and then it causes a dipole in the ones around it. These forces are going to be present in all molecules. Doesn't matter if it's polar or non-polar. You always have London dispersion forces. Sometimes they're just called dispersion forces. Okay. And the tendency of an electron cloud to distort like this is called polarizability. And you might guess that it's easier for something that's bigger to polarize in this way because its valence electrons are a little bit more free to move around. So you can have sort of that instantaneous dipole a little bit easier when the nucleus is not pulling quite so hard on the electrons and when the electrons are a little bit further away from one another. It's not as big a thing when they're on the same side of the atom. With this helium, I mean, this is an extreme example because helium is about as small as they get when you have, well, it is as small as they get when you have more than one electron. These electrons really are not going to like to be on the same side of the atom because that 1s orbital is so small. Those electrons would be very close to one another. But you get up to something a little bit bigger like krypton or xenon, and then you've got electrons that are, you know, in a much bigger energy level, a little bit more room to move around, and especially those valence electrons, then, you know, they can tend to end up on the same side of the atom a little bit more easily. Okay, so the things that affect London forces, and the reason you need to know this is because they ask this a lot on the AP exam. The shape of the molecule is going to affect it. The longer skinny molecules, like this N-pentane here, they have stronger dispersion forces. Okay, and the reason for that is there's just more surface area there, more exposed surface area that can bond with, I should be drawing dotted lines, not solid lines, that can bond with other molecules that are the same. Okay, so there's just more surface area there than there is on something, you know, like the neopentane. Okay, so long skinny molecules, those are going to have stronger dispersion forces. And again, you're going to see lots of questions like this on the AP exam. Okay, and again, it's because of the surface area. The other thing that affects it is as the molecular weight increases, as the size of the atom increases, then typically the strength of the dispersion forces increases. Okay, so as the molecules get bigger, as there are more electrons, as there are more energy levels, then that's going to increase the strength of these dispersion forces. And again, just an idea here, there is no difference in polarity between these because they're all completely non-polar. Okay, same with the noble gases over here. But as you increase the mass, you can see the boiling points go up, which actually explains this. These London dispersion forces explain why, if you look on the periodic table, fluorine is a gas at room temperature, chlorine is a gas at room temperature, bromine is a liquid, and iodine is a solid at room temperature, because those forces get stronger and stronger and stronger. Okay, so that's the idea there. And the reason is, again, I just said this, but larger atoms have larger electron clouds. Those are easier to polarize. Okay. All right. So, question is, which have a greater effect? The dipole-dipole interactions or dispersion forces. And you just sort of have to be aware of the situation that you're in. Okay. If you have two molecules that have comparable size and shape, then you're going to try and look for the one that's more polar, okay? But if you have one molecule that's much larger than the other, then dispersion forces might make the difference there, okay? So you just got to look at the molecules they're giving you. If they're all very similar in size and shape, then probably you're going to look at how polar are they. And the one that's most polar is the one that's going to have the highest boiling point. For example, they ask that a lot. But if you have one that's just obviously much, much bigger than another, and a lot of times they will, you know, if they give you that sort of scenario, then they will make them about the same polarity. Then you're looking at London dispersion forces. Okay, so you just got to pay attention to that. So, sample problem here, dipole moments of acetonitrile methyl iodide. They give you the two dipole moments there. They want to know which one of these will have the greatest dipole-dipole attractions. Okay, so you've got CH3CN and CH3I. And obviously, The one that has greater dipole-dipole attractions is the one with the biggest dipole moment. Okay, 3.9 debye, that's going to be the CH3CN. Okay, and so the CH3CN is the answer on that one because it has the highest dipole moment. Okay, you probably know where this is going from here. Now the question is, which of these will have the greatest London dispersion attractions? So now you just need to look at molar mass, okay? Usually the bigger the mass, the higher the London dispersion forces. And you can probably tell here, you add all of this together, you're going to get a fairly low mass. Nitrogen's 14, each of the carbons is 12, and so you get 24. This is bad. I should be able to do this in my head. 38, 41, okay? So 41 grams per mole here. If you add these up, well, iodine itself was 127, okay? So that's, you know, this is much bigger. So the CH3I, because of its much greater size, is going to have greater London dispersion attractions, okay? So then the question is, the boiling points of the CH3CN and the CH3I are 354.8 and 315.6 respectively. So which substance has the greatest overall attractive forces? And the answer there is just going to be the one with the highest boiling point. The one with the highest boiling point is going to be the one where the molecules are most attracted to one another. They don't want to let go. Okay, so 354.8 Kelvin, that's the CH3CN. So it turns out for this particular molecule, or for this particular set of molecules, this scenario, the dipole moment, the difference in dipole moment is more important than the difference in size. Okay, so the dipole-dipole interactions really determine which one has the greatest overall attractive forces, as opposed to the London dispersion forces on this one. But it's close because these two boiling points are not that far away from one another. Okay, another sample problem here. Pentane has 3 structural isomers. That means they have the same molecular formula but different arrangement. We're going to talk about that more in a couple of days when we talk about organic chemistry. But it's asking which of these 3 would most likely have the highest boiling point. Okay, so if we take a look at this, this is carbon and hydrogen only. And carbon and hydrogen, they do not have a very big difference in their electronegativities. Okay, and actually, if you figure out how all these are arranged in space, this is a very non-polar arrangement. All of these are. Okay, so there's not a lot of polarity in these molecules. So that's really not the big difference here. The big difference is going to come from the London dispersion forces. Okay, now these are all the same size. Also, if you look at this, each of these has 5 carbons. Okay, and the same number of hydrogens, but they just have different arrangements, different shapes. Okay, so the shape is really the determining factor on this one. And it turns out this one right here is the long, skinny chain, which we talked about before. That's the one that's going to have the greatest London dispersion forces. Okay, so that's the one that's going to have the highest boiling point, and it's because it has the greatest dispersion forces, or greatest London forces. I'm even say it. Because it is long and skinny. So there's just more surface area there for it to interact with another molecule of the same type. And those are going to connect to one another a little bit better than the other 2 orientations. Okay, so question here, how do we explain this trend? If you look at CH4, SiH4, GeH4, and SnH4, those are all in the same column, the carbon, the silicon, the germanium, and the tin. And I'm looking at this bottom line right now, this one. If you look at all of those, then they're all in column 4. Okay, and the trend is kind of the way that you would expect it to be. The higher the molecular weight, the higher the boiling point. Okay, and same with the hydrogen attached to some different things that are in group 6. Okay, you've got H2TE, H2SE, H2S, and then you got this crazy anomaly here, the water. Okay, and so the question is, why is it that the water has a such higher boiling point? Because it has a smaller mass. So you would expect it, based on this trend, the water to be somewhere down here, maybe. But it turns out you have to get water up to 100 in order to get it to boil. And you might know the answer to this question. The answer to this question is actually the other type of intermolecular force we haven't talked about yet, which is hydrogen bonding. Okay. So when hydrogen is bonded to nitrogen, oxygen, or fluorine, NOF, N-O-F, then it's an unusually strong bond. Okay. And the reason for that is, with those three particular molecules, they're all very electronegative. Okay. And so, I should say the oxygen, the nitrogen, and the fluorine are very electronegative. Okay, so they are going to pull especially hard on the electrons and have a fairly strong partial negative charge, which gives the hydrogen a fairly strong partial positive charge. Okay, so then you have another molecule over here with a very strong partial negative charge, and this bond right here turns out to be very strong because of those very strong partial positive and partial negative charges that you have. Okay, and so this only happens when hydrogen is bonded to nitrogen, oxygen, or fluorine. Okay, it's the only time that this can happen. So this is hydrogen bonding, and hydrogen bonding has a big impact on the boiling point, and also on viscosity and vapor pressure and those sorts of things. It has a very strong influence on those things. Okay, and so because these are kind of special in their strength, we give them their own special name, hydrogen bonds. Okay, and again, it's because of the high electronegativity of nitrogen, oxygen, and fluorine. The other thing that happens here is, essentially, because this is hydrogen, when it's bonded to one of these things, if the electrons are being pulled a lot more closely to the electronegative atom, like the oxygen, the nitrogen, and the fluorine, then all you have left on the hydrogen is really just a proton. Okay, it's the hydrogen nucleus, and so there are no electrons getting in the way, really, of it bonding with something that has a negative charge. Okay, and so because of its size, and because of the fact that it really doesn't have any electrons at that point because they're being pulled so closely to the other atom, that makes for a very strong partial positive charge that can bond with something that has a very strong partial negative charge. Okay, so sample problem here. In which of the following substances is hydrogen bonding likely to play an important role in determining physical properties? So we've got methane, we've got hydrazine, methyl fluoride, and hydrogen sulfide. Okay, we need to draw Lewis structures for some of these, probably. The first one, I mean, it's fairly obvious that does not have any hydrogen bonding in it, because hydrogen has to be bonded to nitrogen, oxygen, or fluorine, okay, in order for this to happen. So that one is no hydrogen bonding there. Okay, hydrazine, the way that they have this set up kind of clues us in that this is probably the arrangement. Well, make this symmetrical. This is probably the arrangement that we're talking about on this one. Okay. Now again, that's not a complete Lewis structure. We'd have to figure that out. There's probably at least a double bond there on the nitrogen. I'm not too worried about that right now, because what I am noticing is that the hydrogen is attached to the nitrogen here. Okay, so this is a good candidate for hydrogen bonding. You have to have a hydrogen connected to a nitrogen, an oxygen, or a fluorine. So you get another one of these molecules in here. This is going to have a very partial negative, partial positive, and same on this side. So there are a lot of potential places where this thing could do some hydrogen bonding. Okay, so that's a good example of one that would have some hydrogen bonding in it. All right, now methyl fluoride, we got to think about this. CH3F. The one that's listed first is usually the central atom. So if we wrote this out the way we would normally do it, this is how we would write it, right? Now, at first glance, you might think, oh, that has hydrogen and fluorine in it. That's definitely hydrogen bonding. But the thing is, the fluorine and the hydrogen are not bonded to one another. Okay, the hydrogen is bonded to the carbons, and the fluorine is bonded to the carbon. So actually, this is not a good candidate for hydrogen bonding either. Okay, and then hydrogen sulfide, H2S. Now again, there's no nitrogen, oxygen, or fluorine there, so we can immediately cross that one off. That's not going to be hydrogen bonding. So the only one on this list that is a good candidate for hydrogen bonding is the H2NNH2, the hydrazine. Okay, another one here. For any of the compounds in the previous problem that have hydrogen bonds, draw the complete Lewis electron dot diagram of two of the molecules in an orientation that allows a hydrogen bond to form between them. Well, they like to ask this question a lot on the AP exam too, and I think you actually have one of these in your practice problems. So all they're asking you to do here is to sort of orient these things so that the positively charged hydrogens could maybe connect through an intermolecular bond to the partial positively charged, let me try that again, the partial negatively charged nitrogens. Okay, the hydrogens have a partial positive charge, the nitrogens are going to have a partial negative. So when we align these things, I don't know, I'm going to cheat a little bit here. So we've got these two nitrogens, and I'm going to draw it a little bit differently than I did before, just to make this a little bit easier. Okay, and then maybe I'll turn this other one. Let's see, what's the easiest way to do this here? Well, maybe I'll do this. Sorry if you already drew that. And again, I'm cheating a little bit here. But let's say that we have something like this. Okay, and so then you've got this place right here where these hydrogen bonds could maybe form between the nitrogen and the hydrogen. Okay, and so now there's different ways you could have drawn that, but what they want to see, they want to make sure that you understand that a hydrogen bond is going to be, you've got partial negative charges on either the oxygen, the nitrogen, or the fluorine, and you've got the partial positive charges on the hydrogens. Okay, and so those are the things that are going to form the bonds in between them. Okay, so if we want to summarize this, here's just a list of questions you can ask. Okay, so first question, are ions involved? Okay, and if the answer is yes, then you're going to come over here, and are polar molecules and ions both present? So that's going to be a situation like where you're putting an ionic compound into water. Then you're going to have the ion dipole forces. Okay, if there are no polar molecules, if it's just ions present, then we've got ionic bonding. Okay, and ionic bonding is really an example of an intramolecular force, which is why we didn't talk about it here. Okay, but that always is a possibility as well. If you don't have any sort of polar molecules, if you just have ions, then that's going to be ionic bonding. Okay. Now, if there are no if there are no ions involved, okay, then you come over here. Are polar molecules involved? So if the answer is yes, then we have to choose between hydrogen bonding here or dipole forces. Okay. If there are no polar molecules involved, if these are all completely nonpolar, then we're talking about dispersion forces only. Now, again, I want to emphasize here, dispersion forces, even polar molecules like H2S, CH3Cl, or hydrogen bonded molecules like NH3 or HF, those are going to have dispersion forces as well. Okay? But a situation where you would only have dispersion forces would be if you have no polar molecules whatsoever that you're dealing with. Okay? Alright, so BaCl2, H2CO, HF, and Ne in order of increasing boiling points. They like to give you this kind of question too, so this is a good, useful question. So we've got a bunch of things here, and we've got to consider what all of these, the intermolecular forces that are happening on all of these. And again, I think we did almost exactly this thing last year, so you guys should be totally fine on this stuff. Let's see, BaCl2, so using that chart that we just had, these are ions, and there are no polar molecules involved here, so this is just ionic bonding, okay? When we're talking about ionic bonding, or an ionic compound, that's usually going to have the highest boiling point out of any of the substances, okay? And so that's probably going to be our highest. H2 is completely nonpolar, so that's only London dispersion forces. There's an abbreviation for that. CO, carbon monoxide. 2 atoms, different electronegativities, so there's going to be a little bit of polarity there. So that's a dipole interaction. Dipole, dipole. HF, okay, that's hydrogen bonded to fluorine. That is hydrogen bonding, okay. And the neon, again, that's just an atom, so it's completely nonpolar, which means you put a bunch of neon atoms together, and the only type of force you're going to have is the London dispersion forces, okay? All right, so in order of increasing boiling points, the first thing we have to figure out is what has the lowest boiling point. And we have 2 options here. We've got the H2 and we've got the neon that both only have London dispersion forces. And those are going to be the weakest of the forces, all other things being equal. And these are all relatively the same size, with the exception of the BaCl2, but we'll come back to that one because that one's ionic, so that one's kind of an exception anyway. But out of the ones that are actually molecules, they're very similar in size. The hydrogen's a little bit smaller. But that ends up being the determining factor here, okay? Because the hydrogen is smaller, it's going to have the lowest of the boiling points, okay? Because again, if it's just London dispersion forces, the thing that influences those the most as far as how strong their intermolecular forces are, it's their size. And the smaller they are, the weaker their intermolecular forces. So H2 is going to come first. That has the lowest boiling point, okay? Neon is next. Has the next highest boiling point. Then we're going to move to dipole-dipole, okay? And that's usually going to be the next strongest of the intermolecular forces, okay? Now we only have 1 dipole-dipole here. If we had 2, we'd have to figure out which one is more polar in order to figure out which one has the higher intermolecular forces. But here, since there's only 1, that goes next, okay? Then the one that's hydrogen bonded, because that now we're getting up to stronger and stronger forces here. So the HF. And then the one with the highest out of all the boiling points on this list, it's going to be the BaCl2 because that's an ionic bond. And the ionic bonds you always put last. Okay? Okay, now the intermolecular forces are going to affect several of the physical properties. Okay? One that we talked about a lot is boiling point. But there are some others, okay? Viscosity, it affects viscosity. Viscosity is just resistance to flow. In other words, how thick is it? It's another way to think about that. So the thicker it is, the more it resists flowing, the more viscous it is. Corn syrup is very viscous, okay? It's very thick, it flows very slowly, so it has a high viscosity, okay? And notice here, the longer these molecules get, the higher their viscosity gets. Okay, decane has the highest viscosity out of anything on this list. And the reason for that, the only difference in those, it's not polarity, it's just size. So the London dispersion forces are higher in the decane than they are in anything else, which makes them have a higher viscosity. Decane would also have the higher of the boiling points here. Okay? It's related to the ease with which molecules can move past one another, so when you think about that, it sort of makes sense. The more attracted they are to each other, the harder it is for them to flow past one another, and the less liquid-like they are, I guess. Okay? Viscosity is also going to decrease with higher temperature, so the higher your temperature, the lower your viscosity. That's why maybe some of you have parents who put maple syrup in the microwave before using it. You know, some people just like hot maple syrup, so maybe that's why you do it. But the other reason that you might do it is to make it a little bit less viscous, make it thinner, runnier, okay, because then it can pour over your pancakes a little bit easier. Okay, surface tension is another one. Surface tension is why this bug down here in the left corner can actually walk on the water. It's because these water molecules are attracted to one another, and so they pull in at the surface, okay? And so if you look, you know, example of this, a water molecule in the middle of the solution, it's pulled in all different directions by a bunch of different water molecules. But at the surface, this water molecule right here is only pulled sideways and in. Okay, it's not pulled up because there are no molecules on top of it. So that sort of pulls these things in a little bit tighter at the surface, and it creates this tension there where you can actually float some things on top of there. Okay, and then we already talked about boiling point and all that, so we don't need to talk about boiling point and melting point, but those are two really big ones that are also affected. So that's that. I think you guys are going to be fine on the intermolecular forces. Again, it's pretty much all review, so we will see you in class.